Good morning. Welcome to Krishna's classroom. Continue with our uh, analysis, that is the paths taken from Riemann to Lebesgue while developing the new integration theory. Now, this may appear to be quite repetitive, but I believe that the most of the books do not highlight these aspects, which is at the core of the development. It is all there in every book, but unfortunately, there are very few books which possibly, uh, you know, gives it out or highlights it. And this is also required in the sense that for the young uh, students of mathematics who are likely to be creating more mathematics, they should also feel the path along which great ideas have evolved. And that is the objective. That's why I am repeating. I have done it in my series of lectures in the giving all the details about this development. But now, while generalizing this concept of measure or going to general integration theory, I thought that maybe we repeat or we review the path that is taken from Riemann to. Now let us, what we have seen is this: we take an f which is Riemann integrable, we work on this for the time being, but later we can see how far we can, or probably not this sense, and probably a more general function. We take f to be, we take f real value bounded function AB. And what we have seen is that unlike in the development of Riemann integration theory, where we divided the domain into intervals and then developed step functions approximating to this function. So that was a path. So in Riemann we divided the domain of f into intervals and then approximated f with step functions of the type we say we took a step function sx of the form AI, that is the length of the AI, where of course we had is a partition of AB. So we consider these functions AI chi of xi, except possibly for the final, that is xi equal to xn equal to p, where you include that point also. Then for this, we had integral AI this was the definition of integral assets for that. This was an approximation by choosing appropriate values for AI. So in that, you know how it is done. We change the process for developing the new integral. We partition the range of and looked at yn, and of course it covers the whole range of this such that is so. And then looked at the pullback of F inverse of pullback of yi minus 1 yi through F to construct a partition of domain. Then we looked at the two functions. Anyway, what you call say what you call step functions. Sigma yi minus 1 and sigma this is actually characteristic function. Characteristic function yi and yi times the characteristic function of these two functions approximate f from below and above. Perspective. Taking Riemann integration, we obtain two approximations. By it's called the length of and from below, from above by This was the strategy. Now the problem that you encounter here are, see, f inverse of yi minus 1 yi may not be reversed. It's not. It's an interval. It is the difference between the endpoints. Otherwise, you don't know. Just don't know it. Unless you try to attribute something. Therefore, the problem is, so hence the question is, how to define a length. And that this is the question. So we are now faced with a new problem, namely defining the concept of length for such sets. And if that is done, then in a way we are, if we can, work with the same type of arguments as you have for the development of Riemann. What we follow in the case of Riemann. So that is the first task. Okay. Therefore, what we do is, and we also would like, if we would also like this length to coincide well, this length whenever whenever is an interval. Now that the purpose is that we are going for a extension of Riemann integration theory. That's our task. This is the important part. Come a genuine extension of and that's what we want. We are going from Riemann integral to a new integral. At the same time, the new integral is much sharper than the one that looked at, thereby making all Riemann integrable functions integrable in the new scheme, giving the same value for the integral. At the same time, possibly accommodating far too many functions or far more functions which do not come under the Riemann scheme. Okay, so that's what you mean by an extension. As you have seen that our problem was RAB is not complete. That means more functions are brought in. How to get these more functions into the class, integrable class? At the same time, it should be a genuine extension of RAB. That means all Riemann integrable functions should be integrable under the new scheme, and the new integral of such functions should be equal to the Riemann integral. So that's the whole purpose. Okay, so it's a genuine extension of Riemann integration theory. Now see how this is achieved. Okay, so what do we do in a general scenario? We would try to build or try to attribute a length to every subset of every subset of if that is possible. Such that it gives the length for intervals. So how to do this and what problems you encounter? Okay, so you see that this is the task, and there I am not going into the just giving the basic ideas so that you understand what is happening while going through the various results that follow. to substantiate what we have. So that is the important thing. Okay. Intervals. So start with ABM. The top. Okay. It may be even empty. Now what we do is the following. We try to pack, see, we try to pack this set of question is it possible? Possibly counter. So given A, one can find a non-empty collection of say collection of countable open intervals. IN such that A is packed inside IN. This is important. Can find countable collection of intervals. Such packings available now. You can upper estimate of Maybe finite or infinite. Given by sigma length of I. This is length of I. So for each such packing, you can get a length. Now, one thing that you observe is that this generates a sequence of numbers. Produce a collection of numbers infinite in some cases. For instance, A is contained in R, and you see that the length of R is in some cases. But non-negative and bounded below that means what you have is this. Okay? Bounded below by 0. Therefore, infimum of exists. Exists. Maybe finite. So we shall denote this okay, that is m star Riemann. Infinity. Where INs are, of course, open intervals. So this infimum exists. So they are all bounded below by 0. In the worst scenario, it could be 0. Or it could be in some cases not equal. For instance, if you start with an interval AB, then you see that this m star of I is then therefore the m star of the set that we consider coincides with the length in the case of an interval. For instance, that is more generally m star of j equal to length of j is an interval of not necessarily open, even if the endpoints are straight. Therefore, you see that the length that we define is, or the what we want to be the length is going to be something that coincides with the standard or the usual length in the case of. Okay. Now we call this m star an outer measure. Just so m star is called star of A is called an outer measure of So we see that m star is essentially a map from that is an extended real valued function. A set of all subsets So now this is defined for all subsets. That's it. At this stage, it looks we are through. Okay. Now, unfortunately, no. But what we can prove is the following. Then, first of all, thing that you observe is m star of a singleton equal to 0. This is subadditive, finitely subadditive. And in fact, what you get is this m star of this is what you call countably m star of an interval equal to the length of interval. Okay. Now the point is this, that if you look at this, we would like to have m star to be such that m star of whenever that is the equality should come. More generally, m star of N AI equals to empty for every I not equal. So this is something that, I mean, these are all from our experience of working with lengths that we have. In fact, this is satisfied when our two intervals are I and j are, we call that intervals that I intersection j length of I union j is equal to length of I plus length of j. So this particular property we would like to retain. It's important. We would like this particular property to be true. Okay. That's our object. More general. Collection of intervals that is I then length of union which may not be an interval. This is equal to that's how we work in the case of lengths. These are standard properties. When this may not be an interval. See, this may not. So this doesn't make sense. Okay. So this way, length of this. Again, I would put it this way. What you call the length of, because it's not an interval, therefore this is not it. Okay, so what you have is this. But unfortunately, this additivity of m star issue. So this is another stumbling. Okay. And in fact, you show that there exist sets which are not measurable. Okay. Therefore, what you want to call the length is something that would like to have this. The desirable thing is that, so if I'm not using out of measure of a m is a function defined from a collection of subsets, so we will designate a infinity, where a is a subset of and subcollection. And what we are looking for is this. Is a element of A for n equal to 1, etc. Countable collection with what more property? For I not equal to j, etc. A is a typical number such that if an is in A and ai intersection is this, then measure of this is the property that has to be preserved. It's desirable to preserve, because that takes care of the property of the basic property of the length. So that whatever you do becomes a genuine extension of the length. This leads to what is called measurability. How do you define a measurable set? Log into if m star of E complete. Now this is a crucial criteria of check measurability. Right? What exactly is this? For every see, we are talking about, first of all, you observe that there could be a lot of confusion about it. We are talking about the measurability of E. Okay? We are talking about the measurability of E. This is the one that we. Okay? What does this mean? This means, let me use a Venn diagram rather than working on R. So, suppose this is the whole of R. Suppose this is your A, an arbitrary subset of R. Then you take E. What is E? E is this. We are talking about the measurability of. Okay. So E actually cuts A into two parts, two disjoint parts. This is A intersection E and this portion. This is A intersection complement. Okay. So it actually splits A into two parts. The property is that, so A is now, we should understand this. A is said to be measurable. Okay. What does this mean? Note that further A intersection B intersection A intersection B complement. This is it. So it has been split into two parts, which is a non-empty union of two sets. Well, a union of two non-empty, have two sets having non-empty intersection. Okay. Now what we are writing is this: M star of A complement. This is what we are writing. Okay, this is what we are demanding. So we are only considering those A for which this is true. So we will write with script A. We define as the set of all A such that E belonging to star such that M star of A equal to M star of A intersection B complements, comma, for every A in other words, your E has a nice cutting problem. E cuts any A into two disjoint parts such that the content of the whole of A is essentially the sum of the contents of A intersection E and A intersection E complement. So E cuts every A nicely in the sense that A intersection and E complements into A intersection E. And such that the content of A by M star is the sum of the contents of A intersection E and A intersection E. This is the okay. So we want a split up of this kind. Do you have such sets? Yes, there are plenty of such sets. That means the cutting set by cutting A this is the point. Means there is nothing like a situation that is in general what you can say. It's less than or equal to. So somehow the boundary gets reckoned, or at least some points the boundary gets estimated in M star. In both the sets. Now, this is so the cutting is not neat. That's the problem. Okay. So such sets. So the set of all T, I think I have already written it. This is the one. So script A. Measurable sets and M of the measure is given by or you have M defined as so we have thrown out some sets which are probably not behaving as you would like them to behave. Okay? Or creates problems. Then the question that arises is, do we have still a large class of sets? Okay. So we have the following: 1, 5, and 0, 2, singleton So this is about singletons. In fact, you see that to take a countable union, singleton sets, this belongs to, and measure of equal to sigma which is equal to sigma. Okay. So we have more general. If E belongs to this collection A, then E complement belongs to it's a very nice breakup that you get. If say mutually disjoint collection of that means the countable additivity. Yeah. So A is so A bracket we will write the following properties. R belongs to An script A. Then we have comma A belongs to a complement. So all these properties are in fact intersection the notation EN. E belongs to script A implies complement, comma. Now intersection now times to that's what these properties are. Then you say it's a sigma algebra. So that's the definition of the sigma. So essentially this collection is a sigma algebra. What one can is this. On script A, M is countably F. Countably additive. Extended real value. A is called the set of all set of all. And what is significant is this sixth property. Measure of interval I, essentially the length of. So M is a genuine extension of the concept of length. whose reach goes beyond intervals. Okay? So we have successfully constructed a class of sets, or in other words, we have now R with it's called the Lebesgue measure space. It's a measure space. Okay? Or Lebesgue measurable space, called a Lebesgue measurable space, and are measurable sets with called the measurable space. Okay. Now, some of the things that you observe from this stage, we want to use to develop what is called the measurable class of functions. Because our primary objective is that f inverse of an interval should be in this class, so that for which you can define a measure. Okay, right? That's our objective. So now, what is significant at this stage is that remark A is not equal to, that is there exists subsets of R which fail to satisfy, fail to properties. That is what are called non-measurable subsets of so we have what are called non-measurable subsets. So I am not going into the proof of that. That's a very standard result which you should look into and convince yourself that there exists non-measurable substance. And that is very fascinating. Okay. So I think we would stop here this lecture and start from the next lecture. We will define what are called measurable functions. So you have a gadget to measure. So using that, we'll measure, we will gauge whether a function is measurable. And for such functions, if possible, we would like to define an integral. So that, see, all your approximations that you are talking about make sense for this kind of things. Measure of what I call measure of f inverse of, or what you call f inverse of because these are the sort of things that are required for our purpose, so that measure of such functions are called measurable functions. So we will explore this in our next lecture. Thank you. Comprehensive. I think I am going to be pretty expanded form. I still have not gone into general measure, but perhaps a analysis of whatever we have done, starting from Riemann to Lebesgue, analyzing the reason to go for such an extension, and then how do we achieve that? And then, of course, we ultimately proved that L1 space, or in fact more generally LP space, in with Lebesgue integrable functions is complete. Okay, so we have achieved whatever we were really wanted to achieve. So we'll just trace those paths. That would give you, in some way, a platform to ask a further question. Can you generalize this idea? So that many situations where your domain set is not a part of R can also be. That's our objective. So thank you very much.